These polygonal graphs, or polygonal notations, turn out to be pretty neat. In fact, I've been using them myself for quite some time, since about high school, in my own endeavors. And one of the cool things I was able to do over the years was teach some fun math art lessons, as I was a substitute teacher across the Bay Area here for a bit. And yeah, I would encourage the students to get through the day's lessons and all the stuff we had to do, so that we could have a neat and fun math art lesson. And they were all very excited about it. It's always neat to see students get excited about math. So yeah, and in the process they got to learn some, albeit rudimentary, number theory, such as modular arithmetic. But yeah, and pretty neat stuff. I mean, it's kind of this sort of experimental, investigative, explorational approach to mathematics that I thought would make a nice supplementary book or the such, for something to put together myself. And anyways, and in the process of putting that together, I ended up, coming across these MRSGSs. At any rate, here's just a quick run through with the fun how to draw a seven-pointed star lesson that I often did for my students back in the day. I would just sort of occupy myself on the board, and I'd start, drawing these seven-pointed stars on the board, just without much effort at all. And they'd be like, "Whoa, how do you do that? Oh my gosh, that's so cool," because these are elementary students. And it was a lot of fun. And I said, "Well, I can show you later if we get through everything." So that's where it began. And so I'd write that on the board if we have time, seven-pointed star lesson. And the first thing we would do, once we got to it, and almost inevitably we would, because they were quite interested in doing so. And so anyways, I'd say, well, first of all, before we start with this harder question about how to draw a seven-pointed star, one of the sort of universally useful approaches to mathematics is to first analyze what you know. So analyze what you know, right? And so this would then be, okay, well, we all know how to draw a five-pointed star, right? In fact, I don't even remember first learning how to do this, to be honest. It seems I was born knowing how to draw a five-pointed star. Like, everybody knows how to draw a five-pointed star. Some students actually remembered. Maybe it's just because I'm too old to remember when I first learned this, but some of them remember. I remembered it in first grade or whatever it was. So, but no, I don't even remember. So I said, okay, well, first draw very carefully a five-pointed star. Make it a nice one, because we tend to make them kind of sloppy. And then I'd say, well, now draw a circle around it, trust me. And not that there's anything wrong with it, but this isn't meant to be any sort of Wicca thing or anything, so don't tell your parents on me or anything. It's just some math we're doing here. And then we have, let's go ahead and label these vertices, because this is math, so we want to know a little more about it from a more intellectual point of view, right? So we're going to start investigating this object. So I told them, label it from 0 to 4. We're going to start with 0. And you can experiment with different labels, starting with 1 or what have you. But I think eventually you will find that 0 works very well. And here's why. So notice when we look at this five-pointed star, one of the first things we will notice, I think, is that the first segment here goes from 0 to 2. So, right? So we count to 2. So we go 1, 2, and connect. So count. Let me try that again. Okay. Count to 2, and then connect. That's the first thing we did. Does it work again? Well, 1, 2, yeah, look at that. Connect. So it seems, if we had to guess already, that we would just repeat this process over and over again until we finish our star. 1, 2, connect. 1, 2, and then so this one, connect. And then one more for the finishing touch. 1, 2, and connect. 1, 2, and connect. So we count to 2, then we connect. And that's using a segment to connect the, of course, consecutive points in our sequence. And so notice when we follow that procedure, we end up drawing a 5-pointed star. So then I said, okay, well, let's try to make this a little more mathematically official, right? What are we talking about when we count to 2? And some would get it. They would say, oh, it's multiples of 2, you know? And then I'd say, yeah, okay, well, let's write multiples of 2, but let's write it in a new way. Some of them might have studied variables already a little bit if they were in some of the later years of elementary school. Some might not have, but it's not so bad. So we're going to let n, you know, be a variable where n is going to be equal to the values 0, and then 1, and then 2, and so on. And we got them to agree, you know. I got them to agree with me that, and each other, that if I multiply any of these numbers by 2, I end up with an even number, and not only that, a number that is over here in our star. If we do that around what I then introduced them to, modular arithmetic, mod 5. And then we're mod 5, of course. Basically, we're only looking at the, as I mentioned in a previous video, just the least non-negative residues, technically speaking, or remainders in the case of teaching this to elementary school students. I might mention the term residue for those who are interested. At any rate, and so we could see that we're basically just taking these multiples of 2 over a modulus of 5, and we end up generating this pentagram, right? And so I said, okay, well that's awesome. Now we really understand quite a bit more about this 5-pointed star we often take for granted. So how about we look more at this challenge question we have before us? How about a 7-pointed star? Ooh, that looks like 7-painted star. Let's try that again. 7-pointed star. And then I'd have them guessing, you know, how do we do that? How do we apply this newfound knowledge of that which we once took for granted? If it's multiples of 2 around a modulus of 5, or a clock with 5, you know, points around it, then what might the 7-pointed star be? Well, maybe let's start a little bit before that. Let's draw that utterly useful clock. Only this time, let's put 7 points around it. And I told them a little bit on how to do that. You want to get these inner points a little closer, because we need to make room for one more point on either side of the middle here. And they would figure that out sometimes on their own. At any rate, and then I said, okay, so now let's just do the same thing. Let's label these guys. 0, 1, 2, 3, 4, 5, and 6. All right? And now we could do a couple of things. One, we could just start drawing it and, you know, trial and error. But let's try to get an educated guess here based on what we found already in the previous one. If it was multiples of 2 last time, what might it be this time? And some would rightly guess 3 times n, or multiples of 3, right? And again, where n is a variable, equal to 0, 1, 2, and so on. And then if it was mod 5 last time, then this is what we would call mod 7, right? And so then we would try that. So with multiples of 2, we counted to 2, right? So with multiples of 3, it should follow that we count to 3. So our process should be count to 3, and then connect. Right, so let me try that. So we get 1, 2, 3, connect. 1, 2, 3, connect. 1, 2, 3, and then let's make sure I'm doing this right. Connect. 1, 2, 3, and then connect. And so nice and easy. You can, if you can count to 3, you can draw a 7-pointed star, basically. Right? So we got 1, 2, 3, and connect. And then from here, 1, 2, 3, connect. Maybe this won't be the best 7-pointed star I've ever drawn, but nonetheless it gets the idea across, I think. And then for the last finishing touch, 1, 2, 3, back to where we started at 0 and connect. So we get a 7-pointed star. And so, yeah, they were all quite pleased with that. Someone would figure out how to do it without, the other part of the lesson. They'd be working on that, as precocious as they might be and all. And so, yeah, but at any rate, and I'd have them explain how they did it, and that would be kind of a way to go on with the lesson that way. All right, and so then, it's like, well, now that we know how to do 7-pointed stars, we have like a process here that we can apply. I bet we could do 9-pointed stars, right? So I bet we could do 9-pointed stars. And some would say, why just odd, And then we'd say, well, you know what? Let's take a look at the even-pointed stars later. They're a little more complicated, it turns out. Well, technically it's prime numbered pointed stars, but we won't worry about that. Anyways, and so we got 9-pointed stars, and just following the same pattern here. Well, first let's go ahead and draw our circle with 9 points. And we do the same thing. So do a little faster on this one. And notice we had 2 points extra over here, so we have 3 over here. Try to keep those equidistant. And also symmetrical across the center here. And it's a nice way to draw 9 points around a circle. At any rate, so then we get, I'll just do these in black this time, 0, 1, 2, 3, 4, and 5, and 6, and 7, and 8, right? And so 0, 1, 2, 3, all the way to 8, and then back to 0 again. And so, if it were, multiples of 2 for a 5-pointed star, and multiples of 3 for a 7-pointed star, then of course it would have to be multiples of, and then they would say 4, and yes indeed, that's correct. Multiples of 4, again where n is equal to 0, 1, 2. Multiply 4 times 0, 4 times 1, 4 times 2, right? Over a modulus of 9, which we notate as mod 9. And then we just go ahead and do it, So you could get the multiples of 4, and I might show them how to do the remainders and such on the previous video. But we'll just, do the count to 4 method here. So it's, count to 4. For the younger students, we would just do the count to 4 for sure. And then, down to about 2nd grade, I even was able to manage this lesson. Maybe first is a little young most of the time. But anyway, so we got count to 4 and then connect. And so 1, 2, 3, 4, and then connect. And then someone catch the pattern. Actually, there's another pattern. If you go to the previous one over here, that's the same as 1, 2, 3, 4, right? And then go to the one right before that one over on this side, 1, 2, 3, 4, right? And then go to the one before the other one on this side, so 1, 2, 3, 4. Right? See what's happening there. And then, again, 1, 2, 3, wait, where am I? 1, 2, 3, 4. So there we go. I'm going too slow to be able to do that method too efficiently here. And then we can go right before this one, right? And then right before this one. Yeah. And then, again, right before this one over here. So it's this one right there. And then right before this one. So it's this one. It sort of spins around in that fashion. And there's a 9-pointed star. And of course you can do that freehand as well as you practice. You just want to kind of keep this notion in mind and you get yourself 9-pointed stars. It's a bit of a mess here, but there you go, you get the idea. And if you use this last process we noticed, you can end up kind of squeezing them together as tight as you can. You get 11, 13, 15, whatever pointed stars. Count them afterward to figure out how many, you know, so that kind of thing. So really fun stuff. And then, you know, as we did that, it was a nice opportunity, if we had time, to talk about, well, you know, we went the other way with this. We were, you know, making 7-pointed stars as our goal, and in order to do so, we looked at 5-pointed stars, right? Right. And so what if we went the other way with that realization? What about 3-pointed stars? Is there such a thing as 3-pointed stars? Right, so 3-pointed. And then they would think about that, right? They kind of questioning their own, let me get that a bit nicer, 3-pointed stars, sort of questioning their own, their thoughts on this, because, well, wait, 3-pointed, isn't it just a triangle? And I'd say, yes, that's right, it's a triangle. Oops, I got the colors switched around, oh well. Right, it's just a triangle, right, where this is 0, this is 1, and this is 2, right? And if we follow our pattern, we had multiples of 2 around a modulus of 5 for 5-pointed, and so these were, technically speaking, right, multiples of 1, right, again, where n is just 0, 1, 2, and so on, around a modulus of 3. Now, some would realize, well, you can actually do multiples of 2 and go the other way. And I'm like, that's right. You can actually do that for the other ones as well. Take a look into that question. That's another good question to look into. How can you design these multiples in such a fashion as to draw the same star but in reverse order, you know, that kind of thing. So at any rate, and then I'd let them know, well, you know, this is kind of a funky looking star, maybe put that in quotes, yeah. And then I'd, you know, let them know about this term that we use sometimes in mathematics, known as degenerate. Yeah, and degenerate is, you know, generally speaking and loosely speaking, a simple case, right? So simple that it sort of, you know, doesn't look like the thing you're talking about usually. And then I'd give them like a degenerate triangle, for example. Would be, you know, instead of a triangle like this, it's a triangle where you've drawn the other sides so close to the third side that it actually looks like what we call a line or a segment or what have you. So this is a degenerate triangle, right? So this is a very useful term in mathematics. It's not infrequent that including the degenerate cases of a particular idea is somehow useful, right? To get a general sort of idea of what's going on. At any rate, so yeah, so that's fun. So we have our degenerate star, the 3-pointed star, known as the triangle. And then, let's see, we, at this point, if we had time, we might also mention, so we talked about the even-pointed stars. If we had time, we'd talk about that. So even-pointed stars. And some of them are already off in their own land, you know, just kind of drawing 33-pointed stars or using rectangles instead of circles, and, you know, to draw their points and connect them, and, you know. At any rate, so those were still following, you know, which was all good if they were doing that too, of course, you know. The whole point of this is to get them excited and, you know, investigating their own ideas and questions. So yeah, at any rate, for those still following along, wanting to get as much knowledge out of me as they could before investigating on their own, yeah, I said, okay, let's draw 6 points around our circle. So we got 6 points, right? So then that means we're in, and I'd ask them, I say mod 6. Very good. That's correct. And then, we'd play around with this idea a bit. We'd say, okay, well, that's cool. Maybe use a different color here. Um, just looking at this, we could say, well, what if we tried to do multiples of 2? So say 2n. Right? And then we just count 1, 2, and we connect. Count 1, 2, and then we connect. And count 1, 2, and then we connect. It's got a nice rhythm to it, right? And then it's like, well, we got all these extra points left over. What's up with that? Well, can we do something about that? And turns out some of them would get it. It's like, oh wait, those are the even numbers, and these are the odd numbers, right? And then I tell them, well, hey, check this out. By the way, a fun way to write down the odd numbers is to write them down like this: 2n plus 1. Because would you agree, I would say, if we multiply a number n equals 0 or 1 or 2 by 2, and then add 1, we get an odd number. And they say, oh yeah, and that's right. And so, in fact, it's true. And I might let them know this is actually a useful way to write down odd numbers in mathematics when we want to talk about all of the odd numbers. At any rate, so, and we just follow the same process, right? So 2n plus 1 would actually start us, if we started with 0, right? We would end up at 1 to begin with, right? And then, let's go back to orange. And then we would go to 3, because we're doing odd numbers. And then we would go to 5. And then we would go to 7, but around a mod 6, we haven't already talked about this already, we would have at this point. We'd go back to here. And they might recognize, hey, I've seen that before. Yes, I think some religions call this the Star of David. I could be mistaken. But, that kind of thing. Again, not trying to preach any particular religion or belief system. It's just math. And we got 2 triangles here. We got the even numbers and we got the odd numbers. And when we do that, we get a 6-pointed star, we might call it, of sorts. At least one version of it. Okay, let's try that again. Having the darndest time with my penmanship this time. 6-pointed star. And then we can say, well, is there any other way to make a 6-pointed star here? And so if any other time left over again in the class, we say, well, yeah, sure, why not, right? What if instead of counting to 2 and connecting, we counted to 3? And this is where it gets really interesting with the notation, right? 4 and 5, right? And then so we count to 3 instead, right? Okay. And we count to 3, so we got 3n and then mod 6 again. And so that would give us 0 going to 3, and then it would just go right back, right? So 1, 2, 3, and then 1, 2, 3. Not exactly what you'd expect from a polygon or star. This might be called a degenerate one of those things in and of itself, yeah? At any rate, and so in this context. And so then we would, continue on. Say, well, okay, well, we did plus 1 last time. How about we do it again here? Plus 1. We get multiples of 3 plus 1, right? And so that would, using the same sort of logic, end us up at 1 to begin with, and then 1, 2, 3. And right there. There we go. And then, looks like we still have a couple more, so we might as well see if maybe we could get that in here too. And, well, if we added 1 last time, how about we add 2? That's right, 2, and then 6. Right, and then so we'd end up with 2, because 3 times 0 is 0, plus 2 is 2, right? And then 3 times 1 is 3, and then plus 2 is 5. So we go here. And look at that, we've just reinvented the asterisk. So, yeah, all that just to reinvent the asterisk. No, I'm kidding. So this is another variation of what we might call a 6-pointed star of sorts. So we noticed at this point, if not before, there might be more than one possible way to do this. And, we might even talk about, if time, the idea or the concept of what is called in mathematics coprime, right? and or also known as relatively prime. Relatively prime, right? And that was to say whether or not two integers share a common factor greater than 1, right? If they do, then they're not co-prime or relatively prime. If they don't, then they are co-prime or relatively prime. And I give some examples, say 4 and 5. Notice 4 is not prime, but 4 and 5 taken together are co-prime. And so if we try, we can, count to 4 around a modulus of 5 circle, right, and get, in fact, a star wherein we don't have to lift our pencil to completely cover every point on the circle. And then, an example of not coprime would be, say, 4 and 6, neither of which are prime, of course. And if they didn't know what prime numbers were, we'd talk about that. But oftentimes they have heard about it at some point. We'd refine it either way. And then we say, well, what's the greatest common factor of these two? Might even say, here's, by the way, a nice little way to write that, GCF of 4 and 6. And then you say, well, it's not 1. We can get better than that. We can go higher than that. We got 2, in fact. Right? And so these are not coprime. And in these cases, we would end up with these sorts of objects here, where we would have multiple disconnected, right, parts of our, quote, star, end quote, right? And so that was the idea. And so that was pretty much where we would end up. And I might say, if there was still time, try it with 8, points around a circle. How many different stars can you get out of that, and that sort of thing. At any rate, it's really a neat sort of lesson. Taught it quite a number of times over the years as a substitute teacher at elementary schools for a while, when I still did that. And so how to draw a 7-pointed star lesson, making use of the polygonal graphs or polygonal notations. And it turns out to be also a really neat way to teach younger folks a little bit about number theory, specifically modular arithmetic, and some of the neat ideas that could come of that, is sort of tied in with such notions as degenerate objects and, coprime, relatively prime, the concept of that. At any rate, so a really neat sort of tie-in with all of this sort of subject matter that I'm going over in this sort of series of videos. So just a little part of the history that led to the MRSGS sort of discovery there.